Okay, so today I'm going to be talking about having a emulator for NILM. So today, basically I've been looking at doing an emulator since the mid 2012, and I kind of had parts of it implemented as part of my thesis and some other journal code. And so I thought, rather than trying to just release a tool, I would actually talk about it and maybe get some good feedback from the community. So today, I guess I'll try to talk for about 15 minutes. I'll introduce my proposed emulator, discuss the goals and the architecture, and I'm hoping that we can get 10 or more minutes of discussion going where I can ask you questions and you can ask me questions. So what is an emulator? Well, emulators are some sort of piece of software that's going to emulate a hardware platform or another software platform. So for instance, having your PC run Apple II games, or having an Android app run in Mac OS. It's not virtualization. So virtualization is taking, say, one operating system and running it 20 times on a single computer. But an emulator can maybe run, say, NILM algorithms in parallel, so we can get accuracy results faster and compare them. There exists a tool called NILMTK, it's version 3. It's good for testing accuracy. It's not an emulator. There's no strict environment control in how an algorithm runs in it. It's good for testing supervised NILM algorithms. And so one question I have is whether I can use my emulator as part of an extension to NILMTK. Okay, so let's just take a look at the overall goal once again, but stated more verbally. So we have smart meters and we have the HAN, which is the whole area network. And we want to be able to emulate the hardware and the communication of those pieces within the home. And we want the algorithm to kind of run in a world-like situation. So I believe that this type of environment would be ideal for testing unsupervised NILM. And by unsupervised NILM, I mean having a NILM model that may have been trained on one house, but the unsupervised part is when you're actually testing the accuracy on a totally unseen house or number of houses. Also, this idea of strict access control. So we want the algorithms to run in a real world-like situation. So no fancy machine learning tricks. You're given data as if you would in the real world. So when a meter sends you data at a certain frequency, you'll get that data in the order that it's given. And also to take into account different sampling frequency rates. So for instance, you may have a meter that does 1 Hertz readings, but then say you also need to have a thermostat, the thermostat's data, and that can happen once every 5 minutes. So the emulator would take care of giving you the right data at the right time. Also, it would be nice to still have this emulator to run on both low and high frequency NILM. But I'll probably look at low frequency first. So again, we want to test in a real world application. We want to test unsupervised NILM algorithms where we're learning what appliances are in a house that we've never seen. And we also maybe want to start looking at high frequency data. We also still want to look at supervised NILM algorithms. So you may still be interested in running accuracy tests on supervised algorithms. So it would be nice to provide a facility so you can compare a supervised algorithm versus an unsupervised algorithm. So when I talk about real-world tests, what do I mean? Well, we're trying to force the algorithm to run like it is in the real world. So for example, say I have a NILM algorithm that relies on a median filter with a sample size of 99. So if my algorithm is looking at 1 minute readings, that means that your algorithm would not be able to give me a prediction till about 1.6 hours after, right? Not say in real time, but 1.6 hours readings after, right? So it gives you an idea of basically whether this algorithm can perform sort of real-time analysis and feedback to occupants within a home. So what components would there be? So there'd be a software version of a smart meter, and there would be a data set importer and converter. So basically what would happen is you can think of the data set as being the cassette tape, and the smart meter, the software smart meter running those data sets in a time series sequential way. There needs to be a way to call the NILM algorithm, a way to test its accuracy or capture the accuracy results, and do this in an encapsulated way. And what we want to also recognize is that if we're going to have a tool, we want it to be, you want to be able to easily integrate your algorithm into it. If it's too complicated, it becomes an adoption barrier. So when we take a look at, say, maybe a system diagram, we have our data sets here. I'm pointing to them with the cursor. We have our software smart meter, which is going to read them in, and we have some sort of emulation programs. Some of them could run in batch, some of them could run single reading at a time and give you feedback. The input is the different algorithms, so we may have more than one that we're interested in testing. We are able to persist the models of those different algorithms for use later on. We measure their accuracy. We put those in logs, and then we, at some point, provide a utility that can give you standard reports. So in terms of the algorithm interface, what we want to do is we want to use very simple inheritance. So basically, if we can expose 4 main methods, right? An init method, which would take your algorithm and do whatever sort of initialization it needed. A test algorithm, or sorry, test function, which would basically give you the readings, and then you would run your disaggregation, and then you would return the results if there's any results to return. A way to persist the model, a way to load the model if it's been persisted. In terms of data sets, what we want to do is we want to have an easy format. So some data sets may have multiple files, right? Some may have a sub-meter file, some may have temperature data, but we want to be able to say what's in those files and how the soft meter would be able to play it back. So we'd have like an overall file that would tell what files exist and where the measurements exist. In this case, we're saying what the ground truth for disaggregation is, which one of those fields are, and then very easy separated value format. Because sometimes it's more system compatible. In terms of the measurements, so what we could do is something like this. You basically, within your algorithm, say what measurements you want. And for instance, in this case, what we're saying is your algorithm can use either current, real power, or apparent power. So either one of those 3 values is okay to disaggregate on, and temperature. And then as the soft meter runs, it would give you values like this: a timestamp. Here's your power reading to 2.51 kilowatts, and give you like energy reading. So basically the kilowatt hour number. And then again for temperature over here, it gives you a temperature value in Celsius. So that's how the software meter would work. It would just give you data sequentially as it's supposed to come if it was in the real world. In terms of output, your algorithm would be flexible in giving what output back. So for instance, in this case, this algorithm is saying it's doing predictions for 2 time steps, and it's trying to disaggregate 2 loads, sub 1 and sub 2. It's determining whether they're on or off and how much watts are being consumed. And the idea is that some algorithms may want to predict in chunks. Some may want to predict single readings. We don't want to limit that. Also, there may be a way to facilitate where you may, at say, some time step, determine the output of an appliance as being 12, but after 3 time steps, you've said, no, it's not 12, it's maybe 11. So one way would be to track the accuracy over time if you're trying to update your estimates. So we still want to look at supervised NILM, and one way to do this is to have a utility that allows us to test a supervised NILM algorithm using some sort of n-fold cross-validation. And one way to do that is just to expose another method called train. In terms of system architecture, what we want is something very simple, right? So all NILM algorithms would exist in a certain subdirectory. You would have a very base implementation that people can use from, and all the other implementations of all the other algorithms would exist there. You have things like a place to store data sets, libraries that are specific to the emulator, the log files from all your testing, the persistent models, any sort of results reporting, and then a directory for scripts, right? So you may want to automate this testing. So you'll be able to write scripts. And the idea is to include a simulator in the end, and then your executables. So in terms of simulation, it can be a part of NILM, but it would be, or the EMU NILM, but it would be kind of like a phase 2. The problem with simulation, it's very easy to build in bias, and it's very hard to get a lot of data to simulate. So we would kind of look at architecting it as a separate phase. Some ideas are we gather high frequency appliance traces and then we downsample them to low frequency for low frequency NILM. We want to carefully design how we randomize different appliances together when we're actually trying to create our synthetic home. And of course, we need to carefully mimic how these appliances are used periodically. We don't want some algorithm that says that you use the washing machine 12 times in one day, right? That wouldn't really make sense. Okay, so I've rifled through this hopefully fast enough. So some questions I have. Well, before that is, I'm hoping I can release this end of December, and this will be written in Python 3.6, and any sort of upgrades to Python, this would always get upgraded. So some of the general questions I have for you is, would you or could you use this emulator? And if no, why?